of y equals x squared from x equals 1 to x equals 3. Okay, let's have a look at a curve. Let's try and draw ourselves some axes. Okay, so we have a curve. Let's there we go. That's a curve. And we want to get the area under the curve from, well, we could say any arbitrary point. Let's say from here to here. Now, how do we get the area under this curve? Well, the curve's not a nice straight line. If it was a beautiful straight line, we could just have a rectangle, couldn't we? In fact, we can estimate that as a rectangle. And hopefully the bit that is under cancels out the bit that's over. And that gives us an approximation of the area under the curve. Of course, if we had multiple smaller rectangles, let's see what we can do about that. Let's say we have a rectangle here, and a rectangle here, and a rectangle here, and lots of these rectangles. Then we can get a better estimation of the area under the curve. And when we say the area under the curve, what we mean is the area between the 2 points that we're interested on the x-axis and the height up the y-axis from the x-axis. So that's this area here. And this area here. Now, if we look at these rectangles, the height is going to be delta y. That is to say, the change in height, y. And the width is the change in x. So for a single rectangle, the area is equal to delta y times delta x. Does that look familiar? It does to me. Remember the slope of a curve is delta y by delta x. And this time the area is delta y times delta x. In fact, if we multiplied the slope by delta x, we'd actually have the original y, the original change in y. Now, if we want to get the true area, or get as close as we can to the true area, the more rectangles we have, and the smaller or the thinner each rectangle becomes, the closer we will get to the actual true area. So we could actually say that it's the limit as delta x approaches 0. So we could actually say the width of each one is little lowercase delta x, and then that's delta y. So it's the sum of all the change in y's multiplied by the tiny little itty bitty bitty teeny weeny width of each rectangle. Now, as we've seen, just as the derivative was delta y by delta x, so the area under the curve is delta y times delta x. If we take delta y by delta x and multiply by delta x, we can get back to the original y. So if we imagine that this curve that we care about is actually a plot of the derivative, so if this wasn't y, but if instead this was dy by dx, then the area under the curve, if we had the whole area under the whole curve, that would actually be the original curve that this was the derivative of. In other words, the antiderivative, or the indefinite integral. So if we take the sum of all the rectangles as the number of rectangles approaches infinity and the width approaches infinitesimally small, to get the area under the curve, we're actually finding the integral. And this is known as the definite integral. And we're looking for between 2 points. With the indefinite integral, we're looking for the whole area under the whole curve, which we can never know for sure because we've got that plus c. But if we're going for the definite integral, we're looking for the integral between point A and point B on the x-axis. And then we can have our curve there, and that's with respect to x. If we're doing y equals some function of x, or whatever the function is of. Okay, so that's how we write the definite integral. So to look for our answer, y equals x squared from x equals 1 to x equals 3, and we want to know the area under the curve, what we're looking for is the definite integral from x equals 1 to x equals 3 of x squared with respect to x. And how do we find that? Well, remember it's basically delta y with respect to x, or change in y. So, and y equals x squared. So we're looking for the integral of x squared dx when x equals 3, because we're looking for the change in y, minus the integral of x squared dx when x equals 1. Okay, so let's go ahead and do that. So the integral of x squared with respect to x is going to be x cubed over 3 plus the constant minus all of x cubed over 3 plus a constant. And in the first instance it's when x equals 3, so I can replace that x with a 3. And I can replace the second x with a 1. Okay. So let's just see what happens when we try to subtract these. We're subtracting 1/3 and then we're also subtracting the c. So if we get rid of the brackets, we're subtracting the 1/3, but we're also subtracting the c. Plus c minus plus c is 0. So the c's actually cancel out. So we can completely ignore the plus c's when we deal with the definite integral. In fact, we call it the indefinite integral because you've got that plus c and you can't be exactly sure what it is, what the indefinite integral is. But with the definite integral you can evaluate it to a definite amount because the plus c's cancel out. And so now we have a very simple expression. So 3 cubed divided by 3 is just 3 squared, which is 9. Or you could say 27 divided by 3 is 9. And that then subtract 1 cubed divided by 3 is just 1 divided by 3. So that's 1 over 3. And 9 minus 1 over 3 is equal to 8 and 2/3. And that is the area under the curve. And the units will be whatever the units are supposed to be for the function. Assuming, of course, you have units. And that's just all there is to it, to the definite integral. Let's work an example just to get some practice going. Find the area under the curve. Let's say f of x equals 2x plus 1. Nice and straightforward. And then we'll say between x equals 0 and x equals 5. Why not? Okay. So to find the area under the curve, we're going to want the definite integral between x equals 0 and x equals 5 of 2x plus 1, excuse my throat, of 2x plus 1 with respect to x. Okay, so let's integrate 2x plus 1 indefinitely. So that's 2x. The x becomes x squared, and then we divide by 2. The 2's cancel, so we just have x squared. And then plus 1, so then we've got, that could be read as 1x to the power 0. So the 0 becomes a 1, so it's 1x to the power 1, and divide by 1, 1 divided by 1 is 1, and 1 times x is just x. So our answer is x squared plus x. So we have 5 squared plus 5 all minus 0 squared plus 0. Oh, well, that's very easy, isn't it? So 5 squared is 25 plus 5 equals 30. 0 squared plus 0 is just 0. 30 minus 0 is 30. So our answer is 30 units. And that's the area under the curve between 0 and 5 of 2x plus 1 with respect to x. Okay, I hope that was helpful. And I think we can call it there. I mean, there's an awful lot to do with regards to integration, but this is integral calculus. And the title of the series was From Straight Lines to Integral Calculus. We are now doing integral calculus, so I'm going to leave you there. In the next video we're going to give the answers to all of the questions in all of the other videos, and that will summarize everything that we've done. So as usual, I'll leave you with a question, and I'll look forward to seeing you in the next video, which will be the last video in this series.